And now we're starting to focus on some real application of statistical inference, of analyzing statistical data, displaying it, and so on and so forth. So in the real world, I know previously we looked at normal distributions, we looked at binomial distributions. Very frequently we talked about the mean, the standard deviation of populations, how the normal distribution represented that. We learned about the z-scores, we learned about so on and so forth, and we learned basically by wrapping things around this idea of knowing about a lot of information about the population, how it's distributed, how the variability is, what the center of it is, and so on. So now we're going to get more into real world. We're going to start to look at how samples from a population behave, how we can interpret them, because in real life, we almost never will be working with a knowledge of what the population mean is, what the population variability is. We're always going to be dependent on taking a sample from that population and trying to interpret from that sample what that population really looks like. Okay, a lot of times you can get fooled. You know, that's why we wind up doing studies, and then later on someone can't replicate that study because our sample, for a number of reasons, including the possibility that maybe our sample wasn't really random, or maybe because our sample is too small, or maybe just because we had bad luck. You know, when we took our sample, we did everything right, but just had bad luck, because when we do these inferences, we usually tie a probability into them. Probability that we would get such an outcome, that this outcome is real, that it really represents the population. So we're going to start looking at that. And one of the places we're going to start, I'm going to go in here. By the way, I just turned this on. I realized that I didn't realize that it wasn't available to you. But if you go into your Blackboard now, you see folder for week 6 for October 16th. And if you go in there, you'll see there's a textbook reading. There's there are 4, I took the lecture, a previous lecture, and broke them up into 4 parts to make them a little more palatable. So you have an antipasto, you have an entree, you have a meat course, and then you have a little dessert at the end, a little gelato at the end, right? So you can break it up into 4 groups, and they're described there as to what they cover. So for now, I'm going to dive in live separately to try and give you, to use an exercise to try and demonstrate what happens when you sample, when you take a sample from a population. Okay, so, and I'm going to go down here, these documents I have in the lab exercises portion of this. One of the documents is called Introduction to Sample Distribution, and the CLT. Anybody know what CLT stands for? No? Oh my goodness. Okay, we're starting from scratch here. Okay, how about you guys online? You know what CLT? How many of you guys remember your high school or college undergraduate statistics well enough to remember what CLT stands for? I'm not getting overwhelmed by responses online either. CLT stands for Central Limit Theorem. Central Limit Theorem is something, is a way of interpreting the way samples behave in relation to the population that they're drawn from. Okay, and we're going to get an idea of what that means as we play with these numbers. So in this Word document that you see here, I have a table, and that table represents 100 samples. Actually, to be honest with you, that table represents our population. We're going to work with this population. This is everybody in our population. Population can be anything. Population can be the population in the United States. Could be all the people in New York State. Could be all the people in Brooklyn. Could be all the people in all the male graduate students in Hunter that are majoring in biology, right? So that could be a population as well. Could be males with diabetes from age 60 to 80, and so on and so forth. So population is how we define it. Okay, in this case, we have this population. We're not going to worry about what the numbers represent. They might be hormone levels, they might be ages, they might be blood pressures, obviously not blood pressures, but they could be anything, but we're not concerned about that right now. I will tell you that these numbers were generated using a tool in Excel that will produce as many numbers as you want, normally distributed. Okay, so in other words, they're going to be more of the numbers closer to the middle values and fewer and fewer and fewer as you get away from those middle values. So basically, this is like this represents a typical normally distributed population. Okay, so in this instance, we can literally go open up Excel if we have these numbers in Excel, and we can actually just ask it to find the average of these numbers. We can find the mean of the population in this case. We don't have that luxury when the population is 1 million people to go out and find and measure everybody in that population, but in this case we can. And in fact, voila, we actually have an Excel file that says population of 100. So I'm going to open up that Excel file. And you guys, if you guys want, you can go do this along with me. I'm hoping a few of you will do it along with me because we're going to do a little bit of an exercise that I'll need some extra help on. Okay, so here is that same population. Now you'll notice the numbers on the outside in red. Those are row, and I didn't use the Excel numbers. I made them bolder here so easier to see. Those are row and column numbers. So of the 100 people in our population, I could identify any particular subject by saying that he's in row 2 and column 6, or row 6 and column 4, and so on and so forth. And I can find that particular person. So for right now, I'm going to work with everybody that's in this population. I'm going to calculate what is the average, what's the mean value for this population. So I'm going to say equals average, parentheses. And of course, as soon as I enter an open parentheses, it's asking me to tell it where's the array of numbers, where are the numbers you want to average, and actually just going to highlight all of these. And the average comes out to a little over 50. Now, another measurement that really tells me quite a bit about a population, as we started to learn about during our last session, is the variability of the population. Variance, and what's derived from the variance by taking square root of the variance, the standard deviation. So I'm going to calculate standard deviation. Okay, and the standard deviation is about 9. So what does this tell us about this population? It tells us, if this population is actually normally distributed, it tells us that it's likely that 68% of the people in this population are going to have a value here between 41 and 59. Why is that? Because empirical rule tells us one standard deviation below the mean, one standard deviation above the mean would represent about 68% of the population. Okay, well, how about if I went 2 standard deviations out? In other words, 18 from 32 to 68. Well, that would represent 95% of the population. Not everybody in the population, but 95% of it. And indeed, if you look, you can see a couple of 69s. If you look close enough, you might find something in the low 30s here somewhere. But here's a 32 over here, for instance, right? But they're not very common in this population, right? As we would expect, given what we know about its center, 50, and its variability, its standard deviation of 9. So we already know something about this population, right? We know how it's distributed. So that's a great luxury, because in real life, we're never going to know that, right? Because we're never going to actually measure an entire population. The federal government's going to make a liar out of me in about a year, because they're in the process of gathering data for the U.S. Census, which they do every 10 years. But that's a very specific instance, and you're probably never going to see that anywhere else. Okay, so how do we find out? If we don't know, if this population is a blank slate to us, how do we learn about it? How do we learn about what the middle is? How do we learn about what the variability of the values? How do we get to understand it? Well, we get to understand it by taking a sample from it. So I'm going to say to myself, I can pretty easily take a sample of size 9, right? Okay, so I can go in here and I can say, without spending a lot of time or spending a lot of money on grant money and stuff like that, I could take a sample of 9, randomly sample 9 people from this population. Now, how am I going to randomly sample 9 people from this population? Well, maybe I'll click that guy, that. Maybe I'll start clicking around on here. Is that truly random? Well, I'm going to have some biases here, right? In other words, if I'm right-handed, I might pick more people on the right side. If my left eye is stronger than my right eye, I might get that. I just might have a tendency to pick towards the bottom, the top, or not very far. I can't depend on myself to truly make a random sample from this. So I need a way to determine how I can randomize my sampling of this population. There's a million ways to do this. One of the ways is that we're going to use right now is I'm going to go to a table, and here's a table right here. Okay, and it's in our documents. This table, actually, they discuss how this table was assembled. It might use a computer program, which is kind of counterintuitive. Like they're using a machine to generate random numbers. It might be from any number of other possible sources. In science, sometimes in science and physics, sometimes they use the rate at which an atomic, unstable material decays, how often it produces a particle or something like that. The random amount of time that or the distribution of time that it produces that particle to generate random numbers. Something in nature, for instance, that might be naturally random. But there's a million ways to do this. In this case, you can read through this and it'll tell you how they did it. But in effect, what they did was they created a bunch of tables with numbers from 0 to 9, 0 to 10 that were generated randomly. Okay, so there are entire books, manuals of this. There are reference materials online where you can get this as well, right? So believe it or not, you have a book full of just numbers, right? And why are these numbers useful? Because if you need to do something that's random, you can then go to this table and get a sequence of random numbers to help you pick or help you assign values randomly. So in our case, I'm going to pick anywhere to start. I could start in the middle, like over here, or I could start on the edge here. I'll start on the edge just to make it easy. Okay, and the first number I come across is 6 and 5. I'm going to use that to represent the row and column number for the value that I'm interested in. Okay, so in our case, 6 and 5. So I can't get both of these on the screen at the same time. 6 and 5, row 6, column 5 is going to be 47. Oops. Right. So I'm gonna select 47. I'm gonna go now back to 65. The next two numbers are 62. 6 and 2 is 62. Amazingly enough. Right. Okay. And the next two numbers are, well, now I can either go 0, 2, or I can go across. I'm going to go across 0, 3. So row 3, 0. So I'm going to do this 9 times. That's a 60. So I'm going to ask you guys to do that as well. Just pick out 9 numbers like this. And you guys online also pick out 9 numbers. And then when you have those 9 numbers, I want you to find the average for those 9 numbers. Okay, I'm gonna continue along the one I'm working on. Okay, where was I over here? 0, 2, 4, 6, 49. Eight, 4, 44. There was 0, 6, 1. 8. 1, 2, 3, 4, 5, 6, 7. Okay, a couple more. 2, 2, 4, 6, 8. One more. Kind of lost track of where I was, but I'll just use whatever I come across here. Okay. Now, between me and you, if you want to just pick them out randomly, I would be perfectly okay with that. Although I'd rather you get the experience of, like, just taking the time to practice this idea of taking a random sample. So I'm going to find the average of my 9 numbers. And the average comes out to be 52. Okay, so if I knew nothing here, I'm going to go down here. If I knew nothing about this population, right? If I knew nothing about this population, my guess now would be that the average is equal to 52. Right? Would I be right? I'd be pretty close, right? I mean, the true average of the whole population is 50. I'd be pretty close. So if you guys would type into you guys online, if you would type in the values that you wound up getting, the average that you wound up getting, and if you guys here could yell out a average. Okay, 46 point, I'm going to call that 8, 46.8. Okay, need a few more. I'm gonna need a few more here in order to demonstrate this. I may cheat and maybe just take a column or something like that while I'm waiting for you guys to come up with some more. Equals average. Is that 9? That is 9. So I know there's many of you on here, so I should be able to get a few numbers from you guys. There's at least about 8 or 9 of you guys online. Even if you have to do it by eye, just pick them out and I hate cheating on this like this, but you're giving me no choice. How much did you get? 52? Okay, another 52. Okay, I'm gonna say that I'm satisfied with what I got. So if you look up behind me or on your screens, you can see that I took 1, 2, 3, 4, 5, 6, 7 samples from this population. Each one of these, we can see each one of these attempts to approximate the population mean. Now, remember, we would call each one of these X bar, X with a bar over the top of it, right? Because we distinguish it from the population mean, which we call mu, right? Which was 50, this would be mu. Okay, so our standard deviation for the population would be sigma, right? Which is 9 in this case. Okay, I'll just type it in, right? So our means for the population is 52, and these numbers are samples from that population of size 9, and we can see that if we look at these numbers, the numbers are much less variable than the actual values themselves. We don't see any 67s in here. We don't see any 32s, because when you average them, it's only possible to get so many low numbers, right? So, or so many high numbers. So in effect, by taking a sample, you mitigate some of the variability in the values themselves. So X bar is equal to any of these, X bar is equal to each one of these is an X bar that we've calculated. Okay, so now let's say to myself that, that's very interesting, but let me see, what's the variability look like for each of these different values? Okay, so I'm gonna take a look at that. I'm gonna say equals the standard deviation. I'm gonna do it over here, so I got a little bit more room. Or better yet, I'll do it out here so I can spread this out. So my standard deviation is going to be equal to, for these values, going to be equal to STDEV, parentheses. And now notice I'm going to take standard deviations, not of the population, but of the values I got each time I took a sample size of 9 and found an average. And the standard deviation is 2.8. Well, it's very interesting that, let me find the average of all these averages. The average of all these averages turns out to be, wow, the average of all those averages is remarkably close to the population average. Well, what about the standard deviation of the values that I got? How does that relate to the population variability? The variability of our sample distribution, our repeated samples, the variability of those values is much smaller than the variability of the population. Anybody want to hazard a guess what's the ratio between these two? It's 3, right? Right. The variability of the sample means is 1/3 of the variability of the population. What was my sample size? My sample size was equal to 9. Well, it sure looks like the relationship between the mean of the population and the mean of repeated samples is that the mean of repeated samples does a pretty good job of approximating the population mean, but the variability of the repeated samples from that population of the same size is much smaller than the population standard deviation. And maybe it's related to the sample size. And in fact, you'll notice that if we take the sample, the population standard deviation, divide it by the square root of the sample size, square root of the sample size is 3. If I take that and divide it by 3, that's what I'm getting here for the standard deviation of the repeated samples of the same size. That's our central limit theorem. That's part of our central limit theorem. Let me get my where did I put that in? Okay. Let me get something to draw on here. Well, why is this important? Why do we care about this? The reason why we care about this is because we've just learned something about how samples perform in relation to the values in the actual population. And I hope I got my graphics pen here. Is it down there? Yep, there it is. Okay. Okay, let's see. Let me move this out of the way. I'll close this. And I'll get rid of this as well. Okay. Okay. Hopefully this is working. Okay, good. So let's take a look at this. So if I look at our original population, okay, we have a bell-shaped distribution. It's a normal distribution. Our mean is 50, and our standard deviation is equal to 9. Okay, if I look at that original population, I see that my sample standard deviation suggests that 95% of the values, 95% of the people in this group are going to have a value, a measurement between 18 below 50, which would be 32, and 18 above, which would be 68. 68% are going to be between one standard deviation and one standard deviation below. If I take a sample, if I take repeated samples of size 9, as we've just demonstrated from this population, what's going to happen? What's it going to look like now? Well, it's also still going to have a mean of 50, but the results of the sample distribution, the repeated sample, the results of means that are repeated samples of size 9 from this population, that's going to be much narrower. It's going to look something like that. And its standard deviation, right, is going to be equal to 3 instead. It's going to be equal to I'm going to call this ST for standard deviation, or SD. Okay, its standard deviation is going to be equal to the standard deviation of the population divided by the square root of the sample size. So if I have sample size 9, that suggests that 95% of the time, when I take a sample of size 9 from this population, that I am going to get a value that's 2 standard deviations below this, but the standard deviation in this case is going to be 9 divided by 3. It's going to be 3. So it's going to be 6 below this, which is going to be 44 to 56. So 95% of the time, our sample mean for this population is going to be between 44 and 56. Well, how about if I take a sample size equal to 36? Okay, what's that going to look like? Well, in that case, again, if we take repeated samples from this population at random of size 36, the mean, half of them are going to be greater than 50, half going to be below, but the mean is still going to be close to 50, going to be approximately 50. Again, it will be normally distributed, except it's going to be even narrower this time. And this time, the variability, standard deviation of these repeated sample means that we took and made a new distribution out of, that standard deviation is going to be equal to the standard deviation of population again over the square root of the sample size. In this case, 36 over 3, 36 over, 9 over square root of 36, which is 6, which is equal to 1.5 or 1.5. So 95% of the sample results are going to be presumably, if we really randomly sample this, a real normal normal distribution population, are going to be between 47 and 53, much closer. In other words, each one of our sample size is going to determine how likely we are to get a result that's close to the true population mean. Okay, that's pretty interesting, right? That we can do something like that. Any questions about that so far? You got to have a question about that, I think, right? You guys get that? Does it make sense to you? Is that a yes? You people that are in here, you can nod up and down. I can't ask them to nod up and down. I have to ask them to type stuff. But yeah, does it make sense to you? Are you guys okay with that? Because it's kind of a fundamental concept. It's got something that's going to like impact everything we do, or at least a lot of what we do from here on. How about you guys online? Are you guys comfortable with that idea that we can create a new distribution by where the numbers are made up of the means of samples we took from a large population? And that now we understand we understand a relationship between that new distribution, that sample distribution, and the original population, the distribution of the original population. Okay, I'll consider your non-replies a sense to that. Okay, so let me clear this out so we don't have to look at that. Okay, so let's go back to this document. Okay, so it's a little of this is going to be kind of rehashing stuff. I'm going to start off by rehashing a little bit that we did previously, which is when we worked with the normal distribution. Okay, because I think we need that kind of refresher in terms of what's going on here. Here we go. Have a new laptop, and it's got like it's got this double touch function in the keyboard. I guess some of you guys said I replace laptops every like 7 or 8 years. And so on my technology that I was using up to this point was a little bit older. So I got a feeling some of you guys have these double touch, deep touch trackpads on your laptops. And you have to, there's like a touch, and then there's you touch a harder touch, and they do different things. I haven't gotten used to that yet. So I'm having a little trouble getting to move windows around and stuff like that, or getting things to copy. So anyway, but I'll get to it. I'll figure it out eventually. Okay, so let's read this problem. If total cholesterol values for a certain population are approximately normally distributed with a mean of 200 milligrams per 200 milligrams per 100 milliliters and a standard deviation of 20, find the probability that an individual picked at random from this population will have a cholesterol between 180 and 220. Okay, so this is a population. So when we talk about 200, a mean of 200, that's mu. That's a population mean, not a statistical mean. So mu is equal to 200. That's also called a parameter. Parameters, mu and sigma are parameters. They represent the values that we know for the mean. X bar and SD, or standard deviation, are values that we know about a sample. Okay, they're called statistics. Okay, so mu is equal to 200. A standard deviation, sigma, is equal to 20. What's the probability that you pick an individual at random from this population with a cholesterol value between 180 and 220? Well, that one I'm not even going to bother to draw because it should be pretty simple, right? Because how many standard deviations above and below the mean is 180 and 220? One standard deviation below, one standard deviation above. We know 68% of the population is between those two values. So the probability we pick one person from this population and they're between those two values is 68%, or 0.68. How about between 160 and 240? Again, that's a nice even number, 2 standard deviations below to 2 standard deviations above. So we can say that's about 95% of the population. So the probability we'd pick somebody and they would have a cholesterol level between 160 and 240 is 95%. Okay, well, how about greater than 225? Well, things are getting a little sticky now. Now I'm going to have to actually pick up a pencil and start thinking about this. Okay, so let's see what we have here. So I'm going to sketch this normal distribution. Yeah, this should be a review. This is review, right? You guys, we've seen this before. Okay, so let's see what the normal distribution looks like here for this population. Okay, and here is the mean is 200, and sigma is equal to 20. Okay, and we said, let's see, 180 and 1 and 2 standard deviations, and this was 180 and minus 1, and this was 160 and minus 2 standard deviations, and this was 220, and this was 240, and so on. In this case, we want to know what's the probability of picking someone from this population that's greater than 225. So 225 would be a little above 220, right? But it's not a nice even number, so we can't use the empirical formula to estimate it. So we're interested in this area here. So to determine what this area is here, when we use our Z table, or when we use Excel, in both cases, our Z table in Excel, if we tell it what the Z value is, how many standard deviations above the mean that this value of 225 is, when we give it that value, the Z tables or Excel will both give us the area to the left of that Z value, right? We're not asked that, we're asked that what's the value above that. So we're going to wind up having to find the area below from the Z score and subtracting it from 1 to find the area that's left behind. Okay, the area that we're interested, greater than 225. Okay, so what's our Z score equal to? Well, it's going to be equal to the value we're interested in, X, minus sigma over, X minus mu over sigma. Okay, so how many we're looking at how many standard deviations. So if we're 200 and 220, that would be 20 over 20, which would be 1 standard deviation. In this case, though, it's 225 minus 200 over 20. 25 over 20 is going to be 1.25. Okay, everybody agree with that? So now what do I have to do? Now I have to find my Z table. And you have one on Blackboard. You have one in the same area there on Blackboard so you don't have to go search around too much. Okay, so let's find our Z score that we're interested in. Z score is a positive number, so it's going to be on this second page. Okay, then we're on the second page, and it's going to be 1.25. So 1.2, and these columns along 1.2 represent the third digit. 0, 1, 2, 3, 4, 5. So 1.20, 1.2, 1, 2, 3, 4, 5 represents an area of 89.44. Okay, or almost 90% is below that point in our distribution. Not quite, but 89.44. So I'm going to go back to our table here. So our Z score, which is 1.25. Okay. Did I inadvertently erase? No, I didn't inadvertently erase. Okay. Z score is 1.25, and this area that's related to it represents represents 89.44%, or 0.8944 if you express it as a proportion. Okay, that leaves, in the area that we're interested in, that leaves 1 minus 0.8944, or about, let's see, 0.1056. Okay, about 10.56%. So the probability that we would pick a random individual from this population and their cholesterol value would be above 225 is 10.56%, or 0.1056 as a probability. Okay, how about less than 150? Well, less than 150, we take our Z score. Z is equal to 150 minus 200 over 20. So that's 50 over 20, and that's going to be equal to 2.5. So we want to know what percentage of the population is below a Z score of 2.5. Let's go back to our Z table. And let's see, that's going to be a negative number though, right? So we're going to have to be on our first Z table. So negative 2.5. 2.50 in this case is 0.0062. So that the answer to this would be 0.0062. 0.0062. Now notice, since I am looking for the area below that value, I don't have to subtract it from 1. Well, how about between 190 and 210? Oh, well, okay, now things are getting a little bit more interesting. I'm going to have to find the area between these 2 points here. How would I do that? 190 and 210. Let me clear this out so I can start fresh. Okay. Okay, and I hope it's worth doing this review, because I want to make sure that we take this carefully, because what we're doing today is kind of fundamental. So 190 to 210. And we're looking for the area between these two. Problem is that when we calculate the z-score here, like the z-score here is going to be 210 minus 200 is 10 over 20. That's going to be 0.5 plus 0.5. Calculate the z-score for 190, it's going to be 190 minus 200 is negative 10 over 20. It's going to be negative 0.5. When I look up those two z-scores, each one of them is going to give me an area from that point down. And this is going to give me an area from that point down. Okay, so one of the things we can do to find the area between them is to calculate the area for this area, plus 0.5, and find what that area is, and see that will represent the area, this entire area from z-score plus 0.5 and lower, which is going to be which is going to be 0.6915. .6915, and the area for a negative z-score, negative 0.5, negative 0.5 is going to be 0.3085. 0.3085. So this is about 70%. This is about 30%. This is the 30% that we're talking about, from negative 0.5 down. So if I take the area that I got cross-hacked in this direction, which is 70%, and subtract this area, 30%, I'll be left with the area between those two values, 190 and 210. So if I just subtract one from the other, 5, 1, 3, 8, 38.35%, a little less than 40%. So this represents the area between 190 and 210. Okay, fair enough. We've done that before. That's kind of review. So now let's move on to what we've been working on today. Okay, how about if you take a sample of size 25 from that population? Okay, now now instead of that population, now I take a sample of size 25. What's the probability that the mean of that sample is larger than 204? Well, how am I going to know that? I mean, how exactly am I supposed to interpret that? Well, we know now that if we know what the population standard deviation is, what the population mean is, we now know that we can understand how samples from that population are going to behave. So I'm going to start with a sample size of 25. I'm going to take a sample of size 25 from this population, except I'm not going to look at it that way. I'm going to look at it, what if I took many samples of size 25 from that population and I created a new distribution? As we noticed before, the mean of these repeated samples is going to approximate the mean of the population. It's going to be 200. So all of these X is going to average out to 200. X bar is going to average out to 200. But the variability, the standard deviation of this new distribution, made up of only the averages from 20 samples of size 25 from that population, well, that standard deviation is going to be equal to the standard deviation of the population divided by the square root of the sample size. In this case, that's going to be equal to 20 divided by the square root of 25, or 20 over 5. It's going to be equal to 4. Okay, so now we now know that the variability, the way that this is distributed, the standard deviation is equal to 4. Okay, so let's take a look at this. So what's the probability that the mean of the sample is larger than 204? Well, 204 is here. Okay, 204 is one standard deviation above the mean for the samples. So the probability that we would take a sample from this population of size 25 is this area in here. Okay, I should be able to figure it out pretty easily because it came up to be one standard deviation exactly. And in fact, if I look at this, one standard deviation below, one standard deviation above is 68%. That means and since it's symmetrical, from the mean to this point is 34%. So that leaves about 16%. 16% of the samples of size 25 will, that we draw from this population are going to be higher than 204 or higher. Okay. So what about the next one? How about what's the probability that the mean is between 192 and 204? Well, 192 is down here. Okay, how many standard deviations away from the mean is 192? Well, 192 minus 200 is 8 over the standard deviation, which is, over the standard deviation, which is 4. 8 over 4 is 2, so that's -2 is our z-score there. Well, 2 standard deviations above the mean, 2 standard deviations above the mean, well, that represents 95% of the population. So I know if 95% of the population is accounted for here, and that this distribution is symmetrical, I know that only 5% is left. And if only 5% is left, it's evenly distributed between this tail and this tail up here. So this tail would be 2.5%, right? So the answer to this would be, this would be 2.5%. That 2.5% would leave 47% between the mean and that value of 190, and 34% between oh, I'm sorry, that's where is it? Am I looking at the right one? Oh, 204. 192 2. Right. So that would be 2.5%. So 16% would be above a z-score of 1. 2.5% would be below a z-score of -2.5. So the area that's left in between them is going to be 100% minus the 16% and minus the 2.5%. Or more accurately, you could look up the z-table and actually calculate them. Okay, so you can do a variety of things to find all these different values. But the important thing is now we understand the different way that a sample distribution, in other words, samples of repeated, a distribution of repeated samples behaves in relation to the population distribution. Okay, so where are we now? We're about 2:30. Okay, I got it. Oops, didn't mean to do that. Okay, so now I'm gonna take a look at an exercise here where we know nothing about the population. Up until this point, I've been describing the population, and then we've been talking about taking a sample from that population. So you already knew what the real answer to this whole thing is, what the population looked like, what population mean was, population variable. You kind of cheated because we knew about it already. In this case, we don't know anything about the population itself. You sample 100 bottles of detergent and find that on average, each bottle will be sufficient for 57 loads. That reminds you, I have to buy laundry detergent. That's a whole other thing. That's a stop at Costco now. Okay. You know that the standard deviation for the entire population of 100,000 bottles is 5 loads per bottle. I kind of cheated there, didn't I? I don't know the population standard deviation, but I do. I don't know the mean for all of the bottles of detergent, but I do know the standard deviation for the entire run of bottles, the entire population of bottles. That's kind of a cheat. Why am I cheating like that? Why am I telling myself I can know that, not know the true mean for all of the bottles of detergent, but I do know the standard deviation? Why am I cheating like that? I'm cheating like that because I want to be able to use that formula that I just told you about. I want to be able to determine what the standard deviation is for repeated samples of a certain size based on what sigma is. So in order to do that, I can determine the sample size, but I need to know what sigma is in order to make this work. I need to know the population standard deviation. Later on, we're going to see that we have ways around that, since really we're never going to know the population standard deviation any more than we know the population mean. So I need to know that sigma. So in this case, I'm giving myself that luxury, that sigma is equal to 5 loads per bottle. Okay, so so first of all, 57 loads. You take 100 bottles, you have somebody use them, they report back to you how many loads they got out of each one of those bottles, and you give it to 100 families, and you report back. They report back how many loads they got, and you find that the average that was reported back of those 100 bottles was 57. And again, we know sigma is equal to 5. Okay, so 57, is that mu or x bar, 57? Give me an opinion. Mu or x bar? Is that the population mean or is that the sample mean? It's a sample mean, right? You agree with me on that? Okay, we don't know how many average loads 100,000 bottles we do. We only know that 100 of them did an average of 57. So that's x bar. 57 is x bar. Is 5 sigma or the standard deviation? Is it a parameter or is it the statistic? Well, we're telling you that that's true for in the entire population of bottles. So that is sigma. This is a statistic. This is a parameter. Okay, so now calculate the standard error for repeated samples from this population of size 100. We took a sample size of 100. What's the variability now of these for a sample size for repeated samples of size 100? Now notice we introduced a new term there, standard error. Okay, so I'm going to take the standard deviation and say that it's equal to sigma, right? Sigma was 5 divided by the square root of the sample size. Sample size was 100. Okay, so it's 5 over 10. So it's equal to 1/2 or 0.5. Okay, so the standard deviation is equal to 0.5. What's that the standard deviation of? It's the standard deviation of the values we would get if we took averages, if we took samples of size 100 and repeatedly took the average of those 100 and made a new distribution to add all of those averages. That's our standard deviation that I have here. In order to avoid confusing it with the standard deviation of the actual population, in this case sigma, or the standard deviation of a single sample, in other words, the standard deviation of these 100 bottles, in order to avoid that confusing it, in other words, if I have 100 numbers here, like 60, 52 number of bottles that they use, 57, 58, 79, 22. If I have that, and I took the average, right? In this case, it came out to 57. If I took the standard deviation of all those numbers, the standard deviation would be approximately 5. It would be approximately the same as the population, right? Because I'm looking at the individual values. But if I look at repeated samples of size 100, find the average, the mean for those 100 values, just like this, and then do it over and over and over again, make a new distribution, that's this standard deviation, which is equal to the standard deviation of the population, sigma, divided by the square root of the sample size. So in order to avoid confusing this standard deviation with this standard deviation, we call this, instead of calling it standard deviation, we call it the standard error of the mean, or just standard error. Okay, so from now on, when I'm talking about that standard deviation, I'm going to call it standard error. Calculate the standard error for repeated samples from its population of size 100, sigma over square root of n turned out to be 0.5. Calculate the 95% confidence interval for the population mean based on this sample. Whoa, there's another new term we just popped up with. Confidence interval. Okay, let me get another piece of paper here. Yep, I got to take the pen off. Okay, so now we're going to take a little leap of faith here. If this is the population distribution, and I look at this population, let's say it's 100, and that's the mu, that's the population mean, sigma is equal to 10. And if I were to take samples, repeated samples of size, let's say size 25 from this population, over and over and over again, get a whole list of numbers over and over again, take a sample of 25, find the mean, put that number down. Sample of 25, find the mean, put that number down, just like we did earlier. And I would create a new distribution from that. That new distribution would have a similar mean. The mean would still be 100, right? But the standard deviation, we're not going to call it standard deviation anymore. The standard error, the standard deviation of all these means that were based on a sample of size 25, the standard error is going to be much smaller than our standard deviation. It's going to be equal to our standard deviation divided by the square root of the sample size, which in this case is 10 divided by the square root of 25 is 5, is equal to 2. Well, what does that tell us? That tells us that 95% of the time, that if I take a sample of size 25, random sample, 25 people from this population, and find the mean, right? If I find the mean of those 25 people, 95% of the time, my sample mean will be between two standard deviations, two standard errors below 100 and two standard errors above 100. Okay, makes sense? Since if I take another sample, if I've taken many samples, if I take another sample and I know that the mean is going to approximate population mean 100, and I know that the standard error or standard deviation for sample means is equal to 2, then I can say that I'm 95% sure that the next one is going to be between two standard deviations below the mean and two standard deviation above, or in other words, between 96 and 104. If I had taken a sample size of 100, well, this would have been even skinnier, right? And I would have been able to say, let's say, then the standard error is only going to be equal to 10 into 10 into 10 is only 1. So I'd be 95% sure that it would be within two standard deviations, or in other words, within between 98 and 102, right? Makes it less and less likely that I'll get an extreme value when I take a sample of a sample that's far from the mean when I take a sample when I increase the sample size. Okay, so So that's pretty interesting stuff, but I'm going to twist that around a little bit. I'm going to say to myself, okay, if that's true in that case, well, if I don't take many samples, I just take one sample. So in the case of our bottles, whoops, I can't make that go away. Let's see. In the case of our bottles, we sample 100 bottles. We get a mean for those 100 bottles of 57. So our X bar, in this case, X bar, our sample of 100 bottles, just simple sample of 100 bottles, comes out to be 57. Okay, the standard deviation for all of the bottles is 5. Now our sample size was equal to 100 bottles, right? So our standard error, our standard deviation for samples of that size now is going to be sigma over the square root of sample size. It's 5 over 10. It's going to be equal to 0.5. Okay, so in other words, we can almost say that, let's think about this. That suggests that if this is really the true sample mean, if this is correct and the true population mean is 57, then I would expect that 95% of my results to be within 2 standard deviations, or be between 1 washing load of the mean 57 that we got from our sample. Well, yeah, but the only problem is that we don't know that that's really the sample mean. We don't really know that that's the population mean. We don't know what population mean is. We're never going to know what it is. But maybe I can turn this around and look at it differently. Perhaps I can say to myself, well, I know that I should get a result when I take a sample size of 100. I should get a result for my sample mean that is with 95% certainty, is within 2 standard deviations of the value that I wind up getting, right? So instead of looking at it in terms of that being the actual mean, I'm going to look at it a little bit differently. I'm going to say to myself, yeah, 57 is probably close to the mean, but I could still, if the true mean could be 2 standard deviations above, 2 standard deviations below, with a certain level of uncertainty. And what level of uncertainty is that? Well, it's the number of standard deviations that represent 95%, right? And when we use when we originally used our assumptions about the empirical rule, we said that represented 95% of the outcomes, or 95% probability is represented by 2 standard deviations. So what I'm going to do is I'm going to say 57 plus or minus 2 standard deviations. What's my standard deviation? In this case, it's the standard error for the repeated samples. 2 times 0.5. So I can say that I am 95% certain that the true population mean is going to be between our X value, X bar that we got from our sample, plus or minus 2 standard deviations or 2 standard errors from the mean. Okay, that's going to be 57 plus or minus 2 times 0.5, or 1, in other words. So we're 95% sure that the true population mean is between 56 and 58 when we do this analysis. And what do I call this? Anybody have any idea what I might call that? Well, first of all, how likely is it that we actually captured the population mean between these two? The probability is, because it's 2 standard deviation below, is 95%, right? And what can we call this range here? A range is our confidence, a range of confidence. That's our 95% confidence interval. Okay, how many of you have heard that expression, confidence interval, 95% confidence interval? Almost universally, when you read a study that involves the analysis of numerical data, a lot of times if somebody takes a sample, we sampled so many children in the Bronx between these ages and in these neighborhoods, and the average blood lead level was 1.34 micrograms per deciliter. And then in parentheses next to that, what would you expect to see? You'd expect to see the confidence interval. So, and the confidence interval might say be something like 1.2 to 1.6 or something like that. So what does that tell you? That tells you that based on their study and the samples that they took, that the average that they actually measured came out to be 1.34 micrograms of lead per deciliter of blood. But that may not be the real mean for the population, but they can tell you with 95% certainty, 95% confidence interval, that the true mean is between 1.2 and 1.6. Okay, so now if they had just told you this, you would know what their sample results were, but you wouldn't know what their level of certainty was. By telling you the confidence interval as well, now you can understand what their level of certainty is, that they actually captured the population mean. So, okay, so 95% confidence that you captured the population mean. If I do this study 100 times, how many times will I actually be right that the mean will be in the confidence interval? Give me a number. I got to make sure you guys are still awake out there, right? If I do this study 100 times and my confidence interval is, I'm 95% certain that I'm capturing my mean each time I do it, what's the likelihood that the true population mean will be how many times out of 100 will the true population mean be between these two numbers that I determined? 95 times. How many times will I be wrong? 5 times. Exactly right. Right? That's the deal here. Right? That's why we wind up with studies that when they try to replicate them, they don't work. Because most of the time, we can't afford to be 100% certain. Most of the time, we can't afford to be 99% certain. Most of the time, we're satisfied with 95% certainty. Right? So that means 25% of the time, we may be surprised by what the actual population mean to be outside of the range that we understood. Okay, so I think this is a good time to take a break. Those online should be able to hear me again. I think you have been for a little bit anyway. And you may have heard that looks like Blackboard is offline right now. And we do have some materials that we need from there. And it doesn't seem like I can get on there. And other people's experiences here are about the same. So I'm going to move on with just some basic other stuff that I want to cover right now. And we're recording again. And okay, so can you guys that are online, can you hear me and see my screen again? Gonna wait for a reply so I know I'm actually talking to somebody online. Again, if you can hear me and see my screen, please type into the chat box. Yeah, I sometimes get fooled about how many people are actually online because you guys are online also. So I have to subtract you from that group. So yeah, I'm not getting any response. Okay, I am recording, so I'll continue. So there is a document on a Blackboard, which is some additional examples of this. This particular document sticks around with the washing machines. I don't feel like talking about washing machines, since this is public. We're talking about public health, not washing. We're not in the detergent business. So I'm going to ignore that. And I'm going to just go on here and I'll make up a problem instead. Okay, so as an example of this, let's say that you were going to, how many guys, any of you guys working on any kind of studies right now, any kind of projects or something like that, where you're collecting data, numerical data? Nothing at all? Okay, all right, so I'll make one up. Oh no, I also have to get this thing reconnected. Okay, so let me go back up here and So let's say that, what kind of study we're nutrition, you guys are all nutrition students, right? Okay. So what kind of study might you work on? You might want to keep track. You might want to do a survey of people, say a survey of seniors, age 65 to 80. And let's give them a gender, female, and they are they are let's say that they are ambulable, and they're at home. They're not under nursing care or anything like that. So we're interested in what their blood, what their, let's say their blood sugar levels are. So we could do insulin sensitivity. We could do a whole lot of other stuff. Let's just simple blood sugar level. Okay, like a pinprick in a machine. So what would you say the averages for some female seniors in that age range would be, if you did a fasting blood sugar level, simple blood sugar level, for adults in that population that are not seniors. They usually use about 100 as kind of like an action level, correct? Am I right about that? Yeah. So maybe the average for general population would be 50. Let's say that we take a sample of 100 randomly selected female seniors in that age range, and we find that their blood sugar level is equal to 70. Okay, so now let's say so 70 is going to be equal to X bar, right? The average for those 100 seniors. Let's say in another study, which was enormous, like kind of like the diabetes version of the Framingham study, but it had tens of thousands of subjects, right? Let's say they had examined this population in that survey 20 years ago or something like that, and they found that the standard deviation for this population for blood sugar level was 10. I'll make it a little bit broader. Let's say it's 20. Okay. So now I'm saying to myself, well, while the average may have changed, I don't think it's any more variable than it was then. So I'm going to assume that this is true for my sample of 100 people, that they're taken from a population that has a standard deviation of 20. Okay. So now, why am I doing that? I'm doing that because I need to be able to calculate a standard error. In other words, what should sample sizes, what should repeated samples of size 100 look like in terms of their variability? And in order to predict that, I need a standard error. And that standard error is equal to sigma over the square root of the sample size. So I need that crutch in order to be able to do that. Later on, we're going to see that there's a way for us to, instead of using the population standard deviation, to use the standard deviation of those 100 people that we sampled to approximate the sigma for the entire population. We make adjustments for it in terms of our confidence in our result, but it's possible for the moment, I'm going to say I know the population standard deviation, but so we understand that's a construct. We normally don't know it. Okay, so what's the standard error equal to? It's equal to 20 divided by the square root of the sample size, which is 100, which is 20 divided by 10 is equal to 2. So now that I know my average for these 100 people is 70, and my standard error is equal to 2, I can say to myself, well, I'm going to publish this information, and in my abstract, I'm going to describe my result. And I'll say my sample size was 100, the average blood sugar level was 70, but people are going to want to know how precisely, how much can they rely on that 70? What the people that were in this study, was their blood sugar level 2 and 310 and 54, and was it enormously variable, or was it not very variable? If it was enormously variable, that gives me less confidence in that number 70. But if these 100 people that we sampled randomly If their blood sugar levels are all close, 65, 80, 72, then we have more confidence that the population mean, right? The real population mean, mu, is close to that 70, right? We've done a pretty good job of predicting it. So how do I measure that? I use the standard. I use what I know about standard deviation of population and ultimately the standard error to predict that. So in my study, I'm going to say as part of my abstract that our sample size was equal to 100, that our mean was equal to 70, but now I want to qualify that 70. And I want to tell them how precisely that I think I know that that 70 really represents the population mean. And the way that we do that is we give them a confidence interval, right? 95% confidence interval. So I need to calculate what that confidence interval is now. How do I calculate it? Well, it's the mean that I got from my sample, plus or minus the standard error, two standard errors to the left and to the right. That's why that plus and minus is there. I'm going two standard errors to the left with minus, two standard errors to the right with on the positive side. Okay, so what's that going to be equal to? It's going to be equal to 70 plus or minus standard error is 2. 2 times 2 is 4. So 66 to 74. In other words, we have 70 plus or minus 4, 2 times 2. Okay, in other words, 66 to 74. That's my 95% confidence interval. Someone reads this, they see, oh, they got a mean of 70. But they're 95% sure the true population mean is 66 to 74. You see how much more valuable that information is instead of just throwing the number 70, and then they have no idea how precisely you know that number. That's great, except all this time I've been lying to you. Why am I using that number 2? I'm using that number 2 because our normal distribution, whether it's a sample or the populations, sample means population, our normal distribution says, when I use the empirical formula, that 95% of the results are going to be between 2 standard deviations below the mean and 2 standard deviations above the mean. Question now, is that really true? Okay, how can I determine if that's really true? I'm going to erase this now so I'll be able to see behind it. Whoops. Okay. And I'm going to go to my Z table. Oops. Okay, here's my Z table. This Z table gives me the areas of a normal distribution. These numbers on the outside, they're all Z values, but the numbers on the inside are all areas in the normal distribution. So when I get a very big negative Z score, it means that there's very little of this blue area left in this distribution, less than 0.03%. If I go to the other end, if I go to a Z-score of 3.49, look how much of the distribution is below that number, right? Almost all of it's below that number. So theoretically, if I wanted to know what the Z-score is that's associated with 95% of the population, the middle 95% of the population, I would just go to the Z-score that represents 5% here, 2.5% here, and 2.5% here, right? In other words, it's the same Z-score on both ends. So I want to know what Z-score represents 2.5% in the lower tail and 2.5% in the upper tail. In other words, the part of the distribution that's outside of my 95%. Based on the empirical formula, you would think that that's going to be 2.5, that's going to be a Z-score of 2. Right, 2 standard deviations. Let's see what it really is. So I'm going to, instead of going to the numbers like 2, if I go to 2.00 is 2.28%, not 2.5%. So I'm going to go to the areas inside here. And I'm going to look for 2.5%. Here's 2.5% here, right here. What is the actual Z-score that represents a 2.5% being below that and represents really the Z-score we want to use for a 95% confidence interval? It's 1.96, not 2. Well, how about on the other end? 2.5% on the other end. That's going to be 97.5%. 97.5%, leaving 2.5% behind, is over here, and that's going to be also 1.96. Obviously, that's got to be true because it's symmetrical. Okay, so let me go back here. So if I go back to my little construct here, okay, and I said my mean for my sample was 70, and standard deviation of the population was 20, and my sample size was 100, right? If I then said, okay, well, my standard error then is equal to sigma over the square root of n, which is equal to 20 over square root of 100 is 10, is equal to 2. So if I use this and I use this to determine my confidence interval, what am I going to have now? I'm going to have x bar plus or minus my standard error, but now instead of my standard error, I am going to put in the z-score that represents an alpha of 0.05. Alpha means a type 1 error. We're going to be getting to that. Don't worry about it right now. In other words, the z-score that represents a 95% confidence interval. So what am I going to use for z now instead of 2? 1.96. So x bar plus or minus 1.96 times my standard error, which is equal to 2, and that's 70 plus or minus my calculator here. I gotta figure out how to turn on touch here. Okay, let me move this over here so I can see it. Okay, so 1.96 times 2 is equal to that, and I'm going to multiply that. I'm going to put that in the memory. And I'm going to multiply that by, what was it again? 2. No, excuse me, mistake. That was 1.96 times the standard error of 2 was my answer already. Memory recall. There it is, 3.92. So I need to add and subtract that from my value 70. So 70 minus 3.92 is equal to 66.08. That's going to be the lower end of our confidence interval. And 70 plus 3.92. It's going to be the upper end of our confidence interval, 73.92. So that's what I'm going to report as my confidence interval when I report my results. Okay, now let me ask you something. What if I had said to you, you know, I'm not satisfied with 95% confidence. I want to be 99% confident that when I give somebody that confidence interval, that the true mean is between those two. Okay, so if I say the mean is between 66 and 74, you can look up for a second. If I say the mean is, I'm 95% sure the mean is between 66 and 74, and I say to myself, I want to have more confidence in my confidence interval. What am I going to do with my confidence interval? Make it wider, right? So if I say I want to be 99% confident, what's your expectation of our confidence interval? That our confidence interval is not going to be 66 to 74. Our confidence interval is going to be wider than that, right? And as I'm willing to be less confident, if I'm willing to be only 90% confident, what's going to happen to a confidence interval? It can be you'll be allowed to make it narrower because you're not requiring as much confidence. Wider it is, the more confident you are. You actually capture the true population mean. Okay, so now how am I going to accomplish that? And the way I'm going to accomplish that is that really what I'm saying when I do that, what I'm saying is that I want a z value that I'm using to be so wide that, for instance, when I'm talking about a 99% confidence interval, that only half of 1% is in the lower end and half of 1% is in the other end. So in other words, only 1% is outside of my range of that normal distribution of sample means. So instead of using a z-score of 1.96, I need to use something that gives me an area of 0.05 in the lower end and the upper end. How about a 90% confidence interval? What area can I tolerate in the bottom and the top end for a 90% confidence interval? 5%, exactly, 5%. So let's do that. Let's go back to our table. Let me clear off all this junk. Okay, so let's see where we are in the table now in order to get to 0.5% and to 5%. So if I go down to the lower end here, and I'm going to look for 0.05. 0.005, 2.5, 0.00. Here we go, somewhere between these two numbers, right? Here's 0.5%, 0.0051. Here's 0.00549. It's somewhere between these two numbers. I'm going to pick this one over here. So the z-score I'm going to use is negative 0.258. How about for 5%, 90% or 5% in each tail? And notice that it's going to be the same thing on the other end, right? Symmetrical. So for 90%, I need to find the z-score that represents 5% on the low end. And I'm going to look down here. We go over here. And it looks like it's in between here somewhere. So I'm going to use negative 1.64. Wow, okay. So now I got three values here that I can use. So when I want to be 95% certain, so my 95% confidence interval is going to be X bar plus or minus 1.96 times the standard error, right? Standard error is going to be equal to sigma over the square root of n, right? Sample n is our sample size, okay? And our 99% confidence interval is going to be X bar plus or minus 2.58 times our standard error. And our 90% confidence interval is going to be X bar plus or minus 1.64 times our standard error. And that's it. That's as hard as this gets. So when we're working with a numerical variable, and we want to find the value of its central tendency, its mean, right? We take a sample, we find the mean of the people in that sample, and then we apply this formula to calculate the level of confidence that we have in that. In other words, our confidence interval. And you decide, most of the time, you're satisfied with 95% confidence that when you give those two numbers on either side of your actual mean that you measure, remember that when you take a sample from a population and you get an average, that approximates the population mean, but it rarely will be the actual mean of the population. So you're almost never going to wind up with the exact population mean when you take a sample. So now you have at least a way to say with a known level of certainty that the true population mean is between these two numbers, even though when you calculate your X bar, whatever that number comes out to be, you really can't say if it's a true population mean. You can't even really say how close to the true population mean it is. But now you can say that the true population mean is within the range of two numbers with this level of confidence, with a specific level of confidence. Well, that's great. So now I just want to show you one other thing that you can do with this, and then we'll call it a day. Okay, the other thing is that very frequently you're dealing with, instead of numerical variables, you're dealing with categorical variables. For instance, let's say I were to ask you, do you think Pete Buttigieg did well in the debate last night? I keep hearing his name lately. I don't know why. I just picked him out at random. Do you think he did well in the debate last night? We have 4 people here. I'll get 4 opinions, right? Well, how about if I do a survey of 1,000 people? I do a phone survey, call them up at random. There's actually people doing this right now, getting paid for it. Not much, probably. People actually doing it are probably doing it for minimum wage, right? But the people that are running that are making a lot of money, right? Are running these polls, making a lot of money. So let's say you have 20 people working in the boiler room. You tell them each one of you call 50 people. I want results on this. And these are all the questions buried in this question on Pete Buttigieg. How many think he did? How many you thought favorably of him last night or unfavorably? So they got two choices. Yes, you liked them or you didn't like them, right? So out of those 1,000 people they call, 550 say they liked them. Yes, they did like them. 450 said no, they didn't like them, right? So what proportion of those people that you called had a favorable rating, a favorable impression of Pete Buttigieg in the debate? What's the proportion? 550 out of 1,000, right? 0.55. Everybody agrees with me on that, right? I don't want to go any further unless you agree with me. Okay, now is that the true population of everybody that watched the debate? No, it's just those 1,000 people, right? So I'm going to remember how we boxed off mu. Mu means the population mean. We rarely know it, right? P means the population proportion. Everybody that watched the debate, we're not going to know that ever anyway, right? Because the debate's over. They're never going to be able to get to them again. But I do have the proportion for these 1,000 people. I'm going to put a little cap. You remember, just like I did X bar, I'm going to put a little cap on top of that P. Right? That's how I'm going to indicate that it's the proportion for a sample, not for the entire population. Okay, and similarly, we don't know exactly what the true population proportion is, and we might not likely to ever know it. Okay, so in order to determine, well, what does this mean? Does this mean I can be comfortable that the true population viewed him favorably? In other words, is it over 50%? Well, how am I going to know if it's over 50% or not? Right? Well, let's look at the idea of using a confidence interval for this. In order to do a confidence interval, I would have to say P cap plus or minus, I'm going to say 95% for our purposes, plus or minus 1.96, right, for a 95% confidence interval, times the variability of this result. In other words, a standard error. Standard error for a sample, that's a proportion. I'm not going to give you a mathematical background on it, a theorem on this, but I'm just going to tell you that the standard error when you have a proportion is equal to the square root of the probability of the population times 1 minus the probability for the population over the sample size. Now, we don't know the probability, we don't know P, we only know P cap. But I can justify using P cap here because my sample, when you take a poll or when you do these kind of proportions, your samples are generally very large relative to when you do like blood tests or something like that, right? In other words, you don't have to draw blood to get people to tell you whether or not they like Pete Buttigieg, right? So it's a lot easier to do. So usually I have very large sample sizes here. So we're going to use P cap for this. So what's the standard error going to be equal to? It's equal to the square root of 0.55 times 0.45, 1 minus that, over 1,000. So let's calculate that. I got to get my calculator up. Okay, bring this back here. Clear everything. Okay, so 0.55 times 0.45 is equal to this. I'm going to divide that by 1,000. Is equal to this, and then I'm going to find the square root of that. So my standard error is 0.0157. Remember that number for me. 0.0157. That's my standard error. So let's calculate our 95% confidence interval. Our 95% confidence interval for this proportion is going to be P cap, which is 0.55, plus or minus 1.96 times 0.0157. Okay, let's calculate that now. Bring my calculator back here. So I'm going to take this 0.157 and I'm going to multiply it by 1.96. And that's equal to 0.0308. I'm going to call that point, I'm going to call that 0.031, just for our purposes. That's not to encourage you to round. I'm going to talk about that in a second. 0.031 now, 0.031. So it's 55 plus or minus, I've already multiplied by 1.96, 0.031. So that's going to be 51.069, comma, and 54. I got this wrong now. 54.969. Let's rewrite that. Don't let me do this stuff. It drives me crazy when I write something crazy and then nobody says anything. Okay, I got that right now, right? I have 55. Oh no, I'm sorry, I'm wrong. Again, you're letting me get away with crazy stuff. What about this? It's 0.55. I was right the first time. 0.55 minus 0.03 is 0.519, comma, and added to it, it's 0.581. Okay, are we happy with that? Am I right? Look up at it, tell me I'm right. I'm right? Yes? You're not a,
Is that a 95% confidence interval?
yeah, that's why how do you know it's 95%? Because what am I multiplying my 0.01, my standard error by? 1.96.
Yeah.
Okay? Okay, so that's my 95% confidence interval. So I'm 95% sure that the true population proportion, the P without the cap, is between those two numbers. So am I 95% sure that it's above 0.5? Yeah, if I'm 95% sure that it's between these two numbers, then I'm also 95% sure that it's greater than 0.5. Now, what if I had told you that this came out to, what if our standard error was such that it came out to 0.49, comma, and 0.58? Can I be 95% sure it's not 0.5? Not anymore, because it could be 0.5, because that's in my confidence interval, right? So I can kind of use this to make a judgment. We're not going to really, in the long term, this way, right? We're only going to use it to describe how well we know the mean, but we're not going to really use it this way. We have special tests, t-tests, analysis of variance. These things we're going to learn during the semester to really compare values in one population versus another. But I just want to illustrate to you that this kind of tells us something about how the population viewed p-butagen. Where if I had just said 0.55 was our sample result, then it would be kind of hard to justify that. So now this is where they get, when they do a poll, they say 0.1, they say 55% plus or minus 3%. This is where that plus or minus 3% comes from. Okay, because this is such a mess. Hang on a second here. Let me erase this. Okay. Okay, now, remember I said that it was 0.55 plus or minus 1.96 times our standard error. Okay? This is the amount that I'm adding and subtracting from 0.55 to get my confidence interval, right? Okay, so I'm adding and subtracting that much to get my range. So I'm saying my mean is 55 plus a little bit this way and a little bit that way. What might we call that? We might call that our margin of error. And in fact, in statistics, we do use that term. So this is our margin of error. That's where in a poll, you get a percentage and then you get a margin of error. What they're doing is they're giving you, based on what their confidence interval, they use the range that they think the true population value is. Okay, so we have our confidence interval is equal to either our mean or our proportion plus or minus 1.96 times the standard error for our sample that we got our mean from, or our sample we got a proportion from. And if we want to make it a 99% confidence interval, we use 2.58. And if we want to make it a 90% confidence interval, use a 1.9, 1.64. And you can see that automatically using 1.64 makes it narrower, right? But we have less confidence. And using 2.58 makes the margin of error bigger. So you're adding and subtracting more makes the confidence interval wider. So it gives you a higher level of confidence that you captured the true population mean. Okay? Good spot to call it a day. Okay, and notice that we spent all this time on this stuff and we didn't look at the lecture videos. You should look at the lecture videos when you get a chance. Okay, because you'll pick up more information there. The lecture videos, particularly, they cover material on study design. So as you're moving forward in your career in nutrition and in health sciences, you're going to want to understand how studies are designed, or when they're talking about a cohort study or this kind of study, a retrospective study, prospective study, you're going to want to understand what those things are so that when you're called on to design a good study, that you know what you need to do. Or even if you're reading a study and you want to understand what they really did or how they designed it, you'll be able to do that too. So make sure you watch those videos